Hello and welcome to this session on information retrieval. Today our focus is on relevance and ranking. In 2010, Turney and Pantel made this statement which was really appealing to me. Computers understand very little of the meaning of human language. This profoundly limits our ability to give instructions to computers, the ability of computers to explain their actions to us, and the ability of computers to analyze and process text. Vector space models of semantics are beginning to address these limits. So today in this lecture, we'll discuss how to address relevance and ranking, and specifically we'll talk about vector space models and their role in relevance and ranking. Let me remind you, our course is structured in 6 parts. We discussed query understanding, we discussed crawling, we discussed content processing, indexing, index compression, and now we are discussing relevance and ranking. Of course, there is one more piece remaining, which is evaluation techniques, which we would get to shortly. The role that relevance and ranking plays in this whole system is that once we have the query, we are interested in matching with the documents, and we are interested in scoring these documents so that when we retrieve them, we know which are the top uh, K documents, let's say, so top 10 or top 15, top 20 documents. Given that a web scale search would return possibly millions of documents, we are not interested, or it might not even be feasible to look at all the million documents. So we are usually interested in the top 10 documents, let's say, or top K documents, to generalize a bit further. Hence, relevance and ranking plays a big role in this aspect of ranking. Okay, so this was the simple retrieval problem that we started the course with. Let's say we have a collection with 5 documents having the following contents, and the query is IIIT Sri City, which document will match and why. And we said D5 seems like a good match because every word seems to match with the query. And this aspect of matching can be quantified, and once we could quantify that, we could use that as a score. And further, once we have the score, we could do the ranking. So the context goes something like this. So I have a query. I'm interested in building a retrieval system that could score this query against the document collection that I have. One way to do this is to compare each document with the query and assign a score of relevance, but that seems to be slow. Is there a better way to rank? If you try Lucene, so this is a Lucene tutorial on how to index and query with Lucene. So here is a simple example. I have indexed few files, and if I query for CMI, Lucene is actually scoring each of the documents and presenting those documents in the decreasing order of score. So here you see that file 1 seems to be the best hit with a score of 0.26808. This document has CMI is great as the content in it. So how is this scoring done? That is the focus of this lecture. All right, let's focus a little bit on linear algebra, specifically vectors. What is a vector? A vector is a geometric entity which has a magnitude and a direction. So here I show a vector rooted at the origin. Um, a vector as we call it. If x comma y is our vector of interest, then this figure shows a vector 1 comma 1. Um, how is 2 comma 3 different from 1 comma 1? It has a longer magnitude and a different direction. Nobody stops us from adding more and more dimensions to this vector. So here is an example of a 3-dimensional vector. So you could imagine this 3-dimensional vector as connecting diagonally two opposite nodes of a cube, let's say 0, 0, 0 to 1, 1, 1. We could keep on adding dimensions to this vector. I've drawn these vectors on a Cartesian coordinate system. So we have all the axes perpendicular to each other, and I could have as many dimensions as I want in terms of as many axes on the plane, on the coordinate system. Okay, so here is the interesting thing. A number is just a mathematical object and we have to give meaning to it. So what do I mean by that? Let's go back to our vectors where we simply said there are two axes x and y perpendicular to each other, and one unit on x axis and one unit on y axis refers to a point 1 comma 1, and I can now draw a vector rooted at the origin, meaning starting from 0 0 towards 1 comma 1. But this vector has no meaning in real life, isn't it? So we are the ones who need to give meaning to these kind of vectors. So let's start giving some meanings to these axes. So I'm going to call the x-axis as the Sri axis and the y-axis as the city axis. And if a sentence is given to me such as Sri city, I would count the number of occurrences of the word Sri, and that is the number that I'm interested in on the axis of Sri. So I have Sri axis, and in Sri city the word Sri occurs one time, so I remember one. Similarly, there is a city axis, and in the city axis the number of times the word city occurs is 1, so I mark Sri city as a 1 comma 1 vector. The first time when I saw this idea, it was just amazing to me, and it's so naturally fits to the idea of relevance and ranking, as we would see shortly. um, that everything comes so nicely with this concept. Now let's go ahead and try to fit some more sentences. So let's say I have a sentence triple IT Sri city. I would need three dimensions to fit this vector. The unique distinct words in this sentence are triple IT Sri and city. So I put them on three different axes on the Cartesian coordinate system, and now I mark the number of occurrences is one occurrence of triple IT, one occurrence of Sri, and one occurrence of city. So let's say this is 1 comma 1 comma 1, and I simply draw a vector 1 comma 1 comma 1 in this coordinate system, and then I call this as the triple IT Sri city vector. Let's suppose on the same vector space I want to draw a vector for just Sri city, not triple IT Sri city, just Sri city. What would I do? So this is simply a 1 comma 1 vector on the Sri city plane, as it is obvious here. So if x, y, z denotes the vector in this space, all the vectors in this space, then Sri city vector would be 1 0 1, because it lies on the Sri city plane with 0 units on the triple IT plane, triple IT axis. So what have we done so far? We have learned to represent English phrases on the vector space. So I hope so far everything is clear. Let's revisit a little bit of matrices to complete the story. So let's say we have a query Q, which is triple IT Sri city, and let's say we have a document D1, which is a triple IT Sri city, and document D2 as triple IT Delhi. So if D1 and D2 contain these sentences, and if query contains this sentence, and if we are interested in matching them, then D1 seems to be a better match than D2. We'll come to matching in a bit of time. Now let's try to draw the term document incidence matrix for this setting. So clearly we are interested in looking at the distinct terms here. So that's triple IT, Sri, city, and Delhi in the whole corpus. There are only 4 distinct words. So I put these 4 words in an arbitrary order. This order in which you write them is actually irrelevant, but once you have written them, you need to fix them. So you cannot change this once written, right? So you could write it in any order, but once you have written that, it's fixed. The order is fixed. So now let's take the query, uh, and query has triple IT, Sri, and city, or to be more specific, 1 unit of triple IT, 1 unit of Sri, and 1 unit of city, and there are no occurrences of Delhi there. right? So D1 is same as query Q, so that's 1110. And finally, D2 has triple IT and Delhi, but no Sri City. So that's why it's 1001. So in our vector space model, we would represent query as a vector, a four-dimensional vector, 1110, document D1 as the same four-dimensional vector 1110, and D2 as 1001. So note this point here that given any set of sentences, we could create a sufficiently large dimensioned vector, uh, so that we can see all these sentences as a bunch of vectors in our vector space. So that's the main idea here. Let's test our understanding. Please pause the video here and try to answer these questions. Hopefully have got all these correct. So let me quickly explain what these are. So what is the natural language? So we refer to English here when we say natural language. So what is the natural language equivalent of 0110? So when I say 0110, there is no triple IT and there is no Delhi. So I'm going with this order which I have fixed. So triple IT is the first dimension. So there's no triple IT, there's no Delhi, there is Sri City in it. So this must be Sri City. What is the natural language equivalent of 1001? We have already seen this. So 100, 1001 is triple IT Delhi. Yeah, so there's no Sri City here. So it is triple IT Delhi. What is the vector for Delhi? Okay, so if I just want Delhi, I should have all the other dimensions as 0. So it's 0001. What is the natural language equivalent of the query Q? Well, the natural language equivalent of query Q is triple IT Sri City. Right. So I hope you got all this correct. Let's move on. Can you tell me which of the following are sets? If you said all of them, think again. If you said the third one is not a set because apple, banana, and orange repeat. Yes, a set is not supposed to have duplicate elements or repeating elements. So third one is indeed not a set. But look carefully, there are repeating elements in the second set as well. So I repeats here, and hence the second collection is also not a set. Is the first one a set? If you had looked carefully, indeed, yes, this third one is also not a set because 5 repeats. Okay, so none of these are sets. Usually people are not careful enough and just look for the flower brackets, and anything inside would make a set for them. Well, that's not true. A collection becomes a set when it has only distinct elements. So we call these as bags. So you could put anything in a bag. So any number of fives, any number of apples, any number of bananas, and a bag would hold them. So that's the difference between a set and a bag. So bag is just another data structure which represents collections with duplicates. So uh, the representation that I have been showing you is that of a set of words representation. So let's see what happens when we add more words to the sentence. So we have already seen the example of triple IT Sri City, which we chop into triple IT Sri and City and then put them into axes as 1 comma 1 comma 1. But what would we do if we have a sentence such as triple IT Sri City, comma Sri City, and let's say we do some kind of pre-processing to remove the punctuations, the commas. So once we have removed, we have triple IT, Sri, and City. Still, we have the same 3 unique items. So if we were to put them into a set of words, then we get the exactly identical sets, right? So we get triple IT, the set of triple IT Sri City for either of these cases. So this set leads to the representation of 1 comma 1 comma 1 if either of these were our query. So that leads to the same term document matrix and to the same vector representation. So both of these are the same vectors in a set of words representation. So we are interested in similarity. So let's say we have a query triple IT Sri City and a document triple IT Sri City Sri City, and we are interested in knowing how similar or how relevant this query is to this document. So I need to have some way to measure how close this vector is to the other vector, triple IT Sri City Sri City. One way to do that is using a set similarity measure such as Jacquard similarity. We have already visited Jacquard similarity. Jacquard similarity of two sets A comma B is simply the number of entries in the set that represents A intersection B over the set that represents A union B. Let's take an example. What is the Jacquard similarity between these sets? So set 1, 2, 3 and set 4, 5, 6. And similarly 1 2 3 and 1 2 4 and 1 2 3 and 1 2 3. Please pause this video and work this out. If you have not paused already, please pause and work it out. I'm going to move on with the answers. Okay, there is no similarity between 1 2 3 and 4 5 6, so we simply get a 0 as the numerator measures the size of the intersection between these two sets, and there is nothing in the intersection. We get 0 in the numerator. What about the second example, 1, 2, 3 and 1, 2, 4? Okay, there are two elements in common, so we have 1 and 2 in common. So the size of A intersection B would be 2, and there are 4 elements in total. This is where most people make a mistake. There are not 6 elements in the union, there are only 4 elements in the union. This is a set union, please keep that in mind. So when we take the set union of 1, 2, 3 and 1, 2, 4, we get 1, 2, 3, 4, and there are 4 elements in set union. So in total we get 2 over 4, that is 0.5 as the answer. So the similarity is half. This is a little counterintuitive and you should take a moment to observe this. At the first glance it looks like there is 2/3 similarity between these two sets, but if you apply Jacquard similarity we should get to an answer of half. Okay, in the final case, the union and the intersection are pretty much the same as these are identical sets, so we get an answer of 1. And isn't this brilliant? If we get completely identical sets, we give an answer of 1, and if we get completely disjoint sets, then we get an answer of 0, and for anything in between, we get an answer between 0 and 1. And this suits a measure as of relevance for us. And this is just lovely for measuring ranking and relevance. So now we could use this metric to on a set of sentences and a query to match and give back an answer in terms of zeros, in terms of a range between 0 and 1. Let's try Jacquard similarity between triple IT is great and triple ITD is great. Well, it's not one because this is triple IT on one sentence and triple ITD on another sentence. So can you tell me what the Jacquard similarity would be? Oh yes, indeed. This is same as the 1, 2, 3 and 1, 2, 4 example, just that the first element is changed in this case. So we are comparing the set triple IT is great and triple ITD is great. Only one element of the set changes, and we have already seen in this case the numerator has two elements, the common elements that they are is and great, and the denominator would have four elements, triple IT, triple ITD is and great. So we have 2 over 4 giving 0.5 as the answer. So this sets us up for the beautiful area of study called ranked retrieval. In a ranked retrieval model, we want to model documents as a bag of words, which would later enable us to do the matching and give you a relevant score. Why do we not use a set of words document, and why do we go for a bag of words? We'll see that in a moment. So far I have shown you how to use a set of words model and use Jacket similarity to compute relevance for it. So in a bag of words model, there is a slight difference. If I apply bag of words representation to the same two sentences that we saw before, in the second case, I have two Sris and two cities, and both of them get into my bag. Note the difference between the set and the bag here. So when I now put them um, in a representation, so the set of words representation would give me 1 1 1, whereas the bag of words representation would give me 1 2 2. Yeah, so that helps me in remembering the number of times a particular word appeared in in the sentence, and this is useful when it comes to computing the score of the document for relevance. Okay, so let's move from set of words to bag of words. So we are still interested in comparing sentences, and this time we want to compare the sentences using the angle between the vectors. So let's say I have two sentences, the SSN and the Chennai. The way I would model them would be to define three axes, the SSN and Chennai, which are the only three unique terms here, and then the SSN will lie on the plane which has the axes D and SSN, whereas the Chennai would lie on the plane formed by the axis D and Chennai. Alright, so we know how to draw the vectors. Now to understand the similarity between the vectors, what could we do? Let's take a look. Let's talk about the angle between these two vectors. What is the angle between the and SSN vector, do you think? No marks for guessing. Is of course 90 degrees. So we are on the Euclidean coordinate system with every axis being perpendicular to each other. So the angle between the and SSN vectors are exactly 90 degrees. What is the angle between SSN and Chennai vector? The same. So they are also 90 degrees apart. What is the angle between the SSN and the SSN vector? Well, if you had two DSSN vectors, they have to be lying on top of each other. So there should not be any angular difference between them. So the difference should be 0. So let's quickly get through the mathematical notation. So we are representing vectors as a series of dimensions written in this format within brackets. We put a 1 if the word is present, and we put a 0 otherwise. So in this case, if I have to represent the Chennai and the SSN vectors, first I have to lay down the dimensions. So I need to fix the order of these dimensions somehow. Any order is fine as long as you don't change the order once you have put them down. Right. So I have to say, okay, let's say dimension 1 is the, dimension 2 is SSN, and dimension 3 is Chennai. So I have only three dimensions here. So I have to fix the dimensions first. Remember, and I repeat, the order of these dimensions don't matter as long as you don't change it after you have put it. Okay, so once you put down this order, please do not change it. Now let's draw the Chennai vector. The Chennai vector would be 1 for the, 1 for Chennai, and 0 for SSN. That makes it 1 0 1, and the SSN vector would be 1 1 and 0. Okay, so we are very clear about how to do the vectors. Let's quickly check your understanding here. So let's assume I have two vectors d1 and d2, both of them having only one word Chennai in it. Then on a scale of 0 to 1, how similar do you think are d1 and d2? Well, yes, 1 being identical and 0 being completely dissimilar. Quite obviously, since these are the same terms, they are identical, and on the scale of 0 to 1, they are identical to the extent of 1. How about D1 being Chennai and D2 being Triple IT? On a scale of 0 to 1, how similar are D1 and D2? 0. There is nothing common in them. So now the question is, if we were to use the angle between the vectors to relate to the relevance score as shown in this case between 0 to 1, then we have to somehow map 0 to 90 to 1 to 0. So let's revisit trigonometry to do that. Do you remember how would you do you remember some trigonometric identities which could do this trick? Okay, so let me show you what's going on here once again. Just to revise, for convenience, we convert the angle 0 to 90 to values 1 to 0. When vectors are the same, we want to output 1. When vectors are exactly perpendicular, we want to output 0. So in this case, we want to output 1. In this case, we want to output 0, assuming one of these is a query vector and the other is a document vector. So in this example, both document and query vector are sitting one on top of each other. There's a complete overlap, so the answer should be 1. But unfortunately the angle is 0, so when the angle is 0, I want the answer as 1. When the angle is 90, I want the answer as 0, right? So in other words, for any value from 0 to 90, I want an answer from 1 to 0. So 0 maps to 1 as in this case, and 90 maps to 0 as in this case. So 0 to 90 should map to 1 to 0. How would you do that? The simple trick is to use cos theta. Yes, the favorite trigonometry that we studied in our school days. So we have sine theta, cos theta, and tan theta, and cos theta seem to just do the trick for us. Cos 0 is 1. So if you give me the angle, I can give you the score. So 0 cos 0 is 1 and cos 90 is 0, and this is a monotonic function which serves my purpose. So remember, the shape of the function does not matter to me as long as the function is monotonic. And why is this so? When I'm ranking the documents based on the angle between these documents and the query, as long as a more relevant document scores more than the lesser relevant document, I'm happy. The volume with which it scores more is not significant to me. So take a while to digest this idea. As long as I rank the documents, the score of these documents represent the rank of these documents. Now, it does not matter the margin with which the next document beats the prior document. All it matters is that it has a score higher than the prior document and lesser than the next document in order to rank them in some order. And that's why the shape of the function does not matter as long as it is monotonous, and cos theta does the trick for us. So it converts 0 to 90 to 1 to 0 in that fashion. Okay, but here still lies a question. If I have a collection of documents and I have put them on the vector space, and pairwise I can compute the angles between any two documents. So I have the query vector somewhere and I have all the document vectors. I can find the angle of difference between the query vector and each of the document vectors. I could do this and I'll get some values between 0 and 90. Okay. And now I can take a cosine of that angle. So I would get a value between 1 and 0. That's also nice. So am I done with ranking? Looks like we are done with ranking, but the question is, how would you get the cos theta? How would you compute the cos theta of these documents? So you are only given a collection of documents and you have to tell me the cos theta or for that matter theta as well. So how would you do that? So is there an easier way to compute cos theta? It turns out that there is this dot product formula, again something that we studied in our school. Please recollect that A dot B is the L2 norm of A, or the length of A. So the magnitude of A and the magnitude of the B vector times cos theta. So we know this. So in other words, I can just take these two terms on this side to give cos theta as A dot B over AB. Something like this. So let's say I have a D vector, document vector, which in the bag of words representation need not have just ones and zeros, but could have any number there. So let's assume they are weights W1J, W2J, up till WNJ, let's say. And query is also a vector of term weights, W1, W2, up to Wm. Then the similarity of these vectors is represented as cosine of theta, which is simply dj's dot product with q over the magnitude of dj times the magnitude of q. Okay, so I hope it's so far clear to you. So let's take an example and check if we understood correctly. So we have a query BITS Pilani and we want to match it with the documents D1 and D2, where D1 is BITS Pilani Goa campus and D2 is IIIT Delhi. How relevant are D1 and D2 to the query, and which of these should get a higher match and which of these should get a lower match? Well, quite obviously, we see that there are more overlapping terms in BITS Pilani Goa campus, so D1 seems to be a better match than D2. But let's see if our model also retrieves the same way. So we are talking about the vector space model here, but there are many other models such as the LDA, BM25 and so on. So this is just one way of doing relevance. As usual, we construct a term document matrix. So BITS, Pilani, Goa, Campus, IIIT Delhi. So there are 6 terms, unique terms. The order in which you write down these terms actually does not matter as long as you don't change them after you put it down. So let's fix the order this way. You may come up with a different order, that's absolutely fine. But once you have done the order, you use the same order for representing all the queries and documents. Now let's take the query. Query is BITS Pilani Goa campus. No, sorry, query is BITS Pilani, just BITS Pilani. So there are only 2 terms here, 1 and 1. Everything else is 0. D1 is BITS Pilani Goa campus, 0 for IIIT and Delhi. And D2 is only IIIT and Delhi, and everything else is 0. So how do we do the relevance? We have query Q equals BITS Pilani, document D1 as BITS Pilani Goa campus and D2 as IIIT Delhi. And we have the term document matrix, which we have worked out already. From this matrix, we see that in our VSM Q, the query is 11 and followed by 4 zeros. And D1 is 4 ones followed by 2 zeros. And D2 is 4 zeros followed by 2 ones. Now let's compute the similarity between D1 and Q. So we are interested in computing similarity of each of the documents with the query. So first D1 with Q, that would be the cos theta, where theta is the angle between D1 and Q. And one way to do that easily is simply take the dot product and divide it over the L2 norms of D1 and L2 norm of Q. So if you do this, I hope you remember how to take the dot product. So that's so we multiply each element with the other counterpart. So it's 1 times 1 plus 1 times 1 plus 1 times 0 plus 1 times 0 plus 0 times 0 plus 0 times 0. I was lazy enough to write down the other components which multiply by 0. So leaving them out, there are only 2 terms which result in anything. That's 1 times 1 plus 1 times 1. So that's 2 in the numerator. What about the denominator? In the denominator, I take the magnitude of d1, and we know the magnitude of d1 is simply under root of 1 square plus 1 square plus 1 square plus 1 square plus 0 square plus 0 square, which would give me under root of 1 square plus 1 square plus 1 square plus 1 square, or under root of 4, which is 2. Similarly, the magnitude of q is under root of 1 square plus 1 square, so that's under root 2. So that, if you calculate, so bring up your calculators and calculate this for yourself, you should get a value of 0.71. Let's try what happens when we do the same for D2 and Q. Interestingly, since there are no common terms, the dot product of D2 to Q becomes 0. Why? D2 and Q are here, so you see that 0 times 1 is 0, 0 times 1 is 0, and 0 times 0, 0 times 0 are 0. Whenever D2 has a 1, unfortunately Q has a 0. So again, when we multiply Q's terms with D2's term count, then we get 0 once again. So the numerator becomes 0. No need to compute the denominator. We have the similarity of 0. And this goes exactly well with our intuition, isn't it? So we expected D1 to contribute more to relevance than D2 because there are more overlaps here, and that's exactly what we have modeled. One of the brilliances in the world of research is to take a complicated problem and model them in a simple enough way that meets a purpose, and this is a brilliant example for that phenomenon. Okay, so far we have seen examples where it's intuitive for a human eye to figure out the relevance, but look at this textbook example. It's quite difficult for human eye to make out which document should be relevant to this query. The query is cheap CDs, cheap DVDs, extremely cheap CDs, and the document 1 has CDs, cheap software, cheap CDs, and document 2 has cheap thrills DVDs. It's not clear which of the documents should be more relevant to the query, so let's work out the same way. So first thing we do, we put down the dimensions. One of the ways I prefer to do this is to line them up alphabetically, lexicographically. It's up to you to come up with any order, and as I said, don't change the order after you have put this down. And now let's start encoding the queries in the vector form. So the query is cheap. Cheap occurs 3 times, so I put a 3 under cheap. CDs occur twice, so we have 2 DVDs occur once, and extremely there's no software, there's no thrills, so 0 0. So I hope now you understand how to code this term document matrix. So once you have done this, the next job is to find the similarity. How would you find the similarity between Q and D1? Simply take the dot product 3 times 2 plus 2 times 2 plus 1 times 0 plus 1 times 0. So all these terms are 0, so we can leave out these 4. So it's simply 3 times 2 plus 2 times 2 over the length of Q times the length of D1. So if you multiply, if you work out all these things, you should get 0.86, and if you do the same for D2, you should get 0.59. So we say that D1 is more relevant to Q than D2, and D1 and D2 are relevant to Q with these scores. Now, this kind of way to score helps us to rank documents when we are implementing a search engine. Okay, now, so far everything is nice, but we don't, not that every word is equally important when it comes to doing search. What do I mean? So let's assume there is an at or there is a the kind of words, and these words, let's say we want to count them as stop words, or we don't want to include them in our relevance computation. What can we do? We can still construct the same table, and we can just give a weight of 0. So we can have weights associated with all these terms. So let's say the weights of the other terms are 1 and the weight of the term the is 0. And the moment the weight becomes 0, I take the term frequency. These are the term frequencies. CDs appeared twice in query, so that's the term frequency of CDs in query. So we take these and we multiply with the weight to reduce their impact. So if these should have 0 impact, then we simply make the weight as 0. So this entire column becomes 0. Thereby their impact on the ranking and relevance changes. Now, if we recompute the similarity, you would see that there is no similarity between this and this. So similarity between Q and D2 is 0, and similarity of Q and D1 works out to be 0.71. Yeah, so if the query was, instead of bits at Pilani, if the query was the bits Pilani, and since the the gets 0 weightage, even the query vector would have 0 here, and even the document vector would have 0 here. So thereby we would still not match the bits Pilani with the IIIT Delhi, and we will still give a 0 score. And that's the brilliance of using term weights to calculate relevance. So what have we seen so far? So we have seen that if you have a collection of documents, you can throw them on the vector space and model them as vectors. Once you have the vectors, you have two choices. You can represent these vectors as in the set of documents or set of words model, and you can also represent these documents in the bag of words model. The bag of words model gives us the ability to remember the number of times or the term frequency of each of these terms that appear on the vector. And we use that, and once we have a vector represented in the bag of words model, now to understand how similar or dissimilar these vectors are, we leverage the angle between them. We have seen that the identical vectors will sit on top of each other, whereas completely different vectors would be orthogonal to each other. So the angle should be between 0 to 90. So we wanted to find a way which converts 0 to 90 to 1 to 0. And in that process, we saw Jacob similarity in the set of words way and cosine similarity in the bag of words method. So here I showed you bag of words representation and cosine similarity way of computing the relevance score. And finally, we said that not all terms require the same weight. So we could set some weights depending on the corpus and the language and so on. So in this case, I took an example of setting the weight of 0 to the, and if I do that, I can eliminate the effect of the stop words, for example, in query and documents when we are computing the ranking. So that's a snapshot of what we did today. Hope you understand. Hope you understood everything so far. Okay, now we continue from here. Um, we'll now extend the idea of term weighting a little bit further. The question ahead of us is, what should be the term weights for each of the terms in our document? So, okay, for stop words, I said we could give a 0 weight, but what should be the weight of bits? What should be the weight of Pilani? How would you determine the weight of all the terms? So that's the next challenge in front of us. Okay, let's consider two documents in our index, D1 and D2. So D1 simply says an inverse document frequency factor is some text here. Okay, and similarly D2 has some text over here, and we are interested in assigning some weights to all these terms before we go and vectorize them. The one way to do this is to take the inverse of the document frequency, meaning, so let's take the word the. The appears 3 times in D1 and it appears twice in D2. So what I could simply do is take the inverse of the number of times it appeared. So that's the denominator over here. So it says that count the number of times D belongs to D, such that term T belongs to D, right? So for a document D in our collection, if the term belongs to that document, count those documents. Or in other words, I'm just telling you to count the document frequency. How many documents contain the word D, right? And on the numerator we have the total document count. Yeah, so we have two documents, so n is the number of documents in my collection, or the corpus size. So n is 2 in this case. So n is 2 in this case. So let's take the case of the appears in both the documents. In other terms, I have only two documents and all those two documents contain the word the. So simply I could say that 2 over 2 or log of 2 over 2 in this case gives me an ideal number which I like. It's a small number and a sweet number which is 0. Yeah, so that's how I got 0 as the term weight for the. What's going on here? If you look at it, it becomes intuitive on the second glance, at least. So look at this. Uh, so I told you that we are interested in the inverse of the document frequency. So the document frequency of the is 2 and the inverse of the document frequency is 1 over 2. Yes, so the more the term appears in many documents, if the term appears in many documents, its weight should be lesser because it can now discriminate, its ability to discriminate diminishes. Let me repeat, the ability to discriminate diminishes for a word as it appears in more documents. So those rare words which appear in only few documents have a higher ability to discriminate documents. Yes, so that's The That's the concept, that's the idea behind this formulation. So I could have simply taken 1 over the document frequency, and that would have given me the inverse document frequency. Yes, that would have done the trick as well. But can we do better is the question here. And what's the idea behind taking the document size? Okay, so consider this as a way to normalize your answer. So what can happen for the rarest term? The rarest term would have appeared only once in the entire. We don't care for terms which do not exist in our dictionary at all. So the rarest term would have appeared at least once in one document. So in which case we have this working out to be n over 1, which is n. So the weight would range from n to 1. Yeah, so that's exactly what I wanted. Now when the weight ranges from n to 1 and I want a sweet score ranging from 0 to 1, how could I do that conversion? A simple trick is to simply take a logarithm, and I have log 2 over 2 if n matches, or in other words, if the term appears in every document, I get 0, which makes sense for a weight. And if a document appears in only one document, I simply get log of n. So the range actually moves from 0 to log of n, and everything appears in between them. I can further normalize to get 0 to 1. That's a simple thing to do. Okay, so that's the idea behind formulating inverse document frequency this way. There are better formulations, of course, and there are many formulations to compute the term weight. And this way of doing term weighting is take it as a simple way of doing term weighting. So after you have computed this IDF, remember these are term frequencies, TFs. Now we have seen that for computing the relevance, multiplying TFs with IDFs makes a lot of sense. So we compute TF IDF and we call that as the term, or that as the weighted term. So if I put TF IDF here instead of just TF, then I have incorporated term weights. So that's what I'm going to do. But before I move on, as I told you, there are many TF IDF variants. These are worth studying a bit if you have some time. And they highlight some nice ideas. For example, we have already seen the use of logarithm to do sublinear damping. So we wanted to reduce the effect of moving from n to 0 or 0 to n to 0 to log n, right? And that way we have restricted the range of our answers, of our weights. So that's what we call as a sublinear damping. Logarithms are useful in that. We can also do add one smoothing. Now add one smoothing is to ensure that we never get into a zero result. So in this case I have done a 0.5 smoothing, so added 0.5 to the whole stuff, so this is guaranteed to return at least 0.5. And we usually do this when there is something getting multiplied with this, some term getting multiplied with this, and we don't want this to get 0. And if this gets to 0, then irrespective of what is here, we would always get the answer as 0. So we usually do some smoothing, and in this case 0.5 is used for that. And we also do normalizations, either max normalization or some sort of normalization to get to a beautiful number at the end as a result. So usually if you see the variance, these variants would have these kind of ideas like sublinear damping, add one smoothing, normalization kind of ideas, so that you have nicer manageable numbers which are more intuitive for the task at hand. We will not get into the details of each of these variants. I'll let you go and read about them on your own, but I definitely would urge you to understand these ideas of sublinear damping, advanced smoothing, and normalization. All right, so let's put all our ideas into practice. So we have a query IIITD, and I have two documents. Let's say one is the official page of IIITD, which is D2, and there's a fake page of IIITD D1. And just because the fake page guy wants all the traffic to come to him, he has put IIITD some 4 times, although the original page has only one reference of triple ITD. What happens now? All right, so I'll skip how we made this term document matrix using bag of words model. But after we have done this model, we can apply term weighting to further make this table more effective. That's one concept that we studied. And also notice that there is another problem in this way of formulating things, and that is we are biased towards long documents. Why? So look at this. So if we have these kind of documents, the similarity of this query with D1 tends to be more. So in this case, I'm not applying any term weighting. This is simply bag of words model. And when I try to do similarity, I get a higher value of similarity for Q with D1 than Q D2 with Q. Now, this is not ideal because I don't want my search engine to go to all these fake pages who have seen the official page and who can easily create another copy of the page with pasting the same content twice or thrice or more number of times. Now, what can I do to remove this bias towards long documents? If I were to simplify or generalize my statement, I could say that the way we have formulated relevance, the longer the document, the more favorable our system is to give it a higher relevance score, right? So our system gives a higher relevance score to longer documents. So it prefers longer documents, and we don't like this. So one idea here is to do length normalization. Now, how can I do length normalization? Well, one idea is take the term frequency of a term to a document. So that's how many times a term appeared in the document, and normalize it somehow. So here is one suggestion: normalize it with the length. So let's say average document length over the entire corpus is average DL, the numerator here, and let's assume the length of this specific document dj is length of dj. Then I could do an average over length, let's say that's some factor. I could multiply it with term frequency and that would normalize. So we do add one smoothing and a sublinear damping to it to ensure we have a better factor to work with. And if I do this, so what would I get? So let's compute the average document length in this case. So I have 1, 2, 3, 4 words, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9 words after all this pre-processing of removing periods and commas. So I have 9 plus 4 over 2, that's 6.5. That's my average length. And let's take triple ITD alone, the query term triple ITD, and let's try to find the term frequency of triple ITD in document 1. What would happen? So the term frequency in this case is 4. So I would have just put this 4 in my term document matrix if I were not to do anything. But in this example, I'm going to multiply 4 with a normalization factor, and the normalization factor would be logarithm of 1 plus 6.5, which is the average document length, over 9, which is the document length of D1. And when I do this, you see that I have reduced 4 to 0.94. Similarly, when I try to do with triple ITD with D2, it appears once, but after I multiply this, it becomes 0.42. Okay, so there's we have improved the situation. So look at the gap. So uh, from so this would go as 1 and this would go as 4 in our term document matrix. That's 4 times larger. Instead of that, now I have some terms which is just 2 points something times larger. So 0.94 and 0.42. So we have improved a little bit. So this has lesser bias for longer documents, let's say. So that's all I have for today. So let me recap. We have seen how to do relevance and ranking. We have seen the role of term weights, and we have seen why our system or the vector space model um, prefers longer documents and how to control the bias for such long documents. Hope you understood and like these ideas. Please work out the examples in these slides yourself and ensure that you understand every bit of it. I'll see you soon with with many more beautiful ideas like this. Till then, thank you.